Hello, welcome to this presentation about momentum, impulse, and their everyday applications by the scientists. This is by Luke, in charge of research, quality control, and analysis, Connor, the chieftain of the group, Nick, doing research, film production analysis, and Robert, in charge of research, quality control, and film production. Firstly, we'll talk about impulse and momentum in everyday life. These include car crashes, and it can be involved in many sports, including hitting a golf ball and kicking a soccer ball. Car crashes are when between two objects of great momentum, such as cars, who have great momentum because of their massive mass and high velocity, and when they collide, their momentum falls at an extreme rate because of their extreme decrease in velocity. Hitting a golf ball has accurate applications to in real life with momentum because when a golf ball is hit by the player, it receives a sudden change in momentum, which leads to a short reaction time and the development of a large impulsive force that helps the ball to advance in the forward direction, and it can travel very long distances.
Thank you, Robert. To start, I will be answering the question, what is momentum? Momentum is mass in motion, which means how much mass is in how much motion. Momentum is usually denoted by p, which is a vector quantity. The definition of momentum is p equals mv, in which m is mass and v is velocity. The units are kilograms times meters per second, and momentum is always a vector quantity. As Robert previously explained examples of momentum and impulse, but I will add another one, which is a ball rolling on a surface, which its momentum would be the mass of the ball times how fast it is rolling. Next, I want to answer the question, what is impulse? Impulse is a force acting over time, which is impulse is denoted by J and equals the average force times the change in time. Another example of impulse that I could add to Robert's previous explanations could be someone hitting a baseball. The impulse would be the average force that the bat exerts on the baseball times the time that the baseball and the bat were in contact.
Hi, I'm Nick, and I'm just going to be explaining the equations that we used in our experiment, which are the conservation of momentum theorem and the impulse momentum theorem. So if we go step by step through the conservation of momentum theorem, we get the mass of the first system times its change in velocity over its change in time is equal to the opposite of the mass of the second system times its change in velocity over its change in time. Now, if we write this using our variable of momentum, we have the first system's final momentum minus its initial is equal to the opposite of the second system's final momentum minus its initial. Doing a little algebra and rearranging, we can write this as the first system's final momentum plus the second system's final momentum equals the first system's initial momentum plus the second system's initial momentum, which will give us our final equation of the final momentum is equal to the initial momentum. If we apply this to real life, we can see as two cars collide and they continue on moving, we see that their momentums at first could be going opposite directions as they have different velocities and masses, but as they come together and they start sliding together, they'll have inverse effects upon each other, equaling out. Okay, moving to our second equation, we have the impulse momentum theorem, which just states that the directional impulse is equal to the change in momentum. So if we look at our first example of the two cars colliding, we can see that the impulse force is the exact moment when those two cars collide and then start sliding. Or we can look at a different example with a golfer hitting a golf ball. As soon as he comes in contact with that golf ball, that impulse force is going to send the golf ball flying into the air and change its momentum.
for explaining those complex equations. And I'm going to tell you guys how we put them to the test. So we tested the momentum and impulse equations in two different lab setups. We had a momentum lab setup and an impulse lab setup. So with the impulse lab setup, we had a blue car that had a 250 gram weight on it, touching a force probe. And the side that was touching the force probe had the explosion happening on it. So we would have a group member essentially click a button on the car, which caused a plastic rod to shoot out of it, therefore simulating an explosion reaction. And we used the little green motion sensor, as you see, to measure the velocity that the car was traveling at. With the lab setup, we had both a red car and a blue car with a 250 gram mass on each of them. So we'd have someone push the red car into the blue car in a completely inelastic collision, meaning both the cars would stick together when they collided. So someone would push the red car while someone was also slightly pushing the blue car.
Go.
So our data, what we were trying to prove was the conservation of momentum, and that the you can see that we graphed impulse on the y-axis versus the change in momentum on the x-axis. And we had about a 3.3% error, as you can see, as our slope is 0.977, which means we were pretty close to showing that the change in momentum is equal to the impulse. And then on the other hand, we have the conservation of momentum graph. So essentially we had the change of momentum of the red car on the x-axis and the change in momentum of the blue car on the y-axis. We also tried to show that both of them, the changes of momentum in both of the cars were equal, and we had about, again, a 3% error there. So I would say that our experiments were pretty good. Thank you so much for watching our YouTube video and listening to our experiment, and we hope that we helped you guys learn a little more about physics. Thank you.